All right, this version of Notes for 1.3 is designed to be used with the ALEKS homework that we've got at Elkridge, but it could be used by anybody wanting to solve exponential equations using, let's write this in here, using the equality property. So the equality property. So quick warm up here, just a reminder of some common exponential expressions. So 1 to the second, remember this is the base and this is the exponent. Sometimes we'll write it like that, b for base, x for exponent here. So the exponent tells us how many times we use the base as a factor in a multiplication problem. So we're going to use the 1 twice. So this literally means 1 times 1. So we've got 1 for an answer there. Use the 5 twice. So that's going to be 5 times 5. So that'll be 25. 7 squared. Use the 7 twice. So that's going to be 49. Again, we're not multiplying the two numbers together. We're multiplying 7 by itself twice. And then 11 squared, 121. 8 squared is going to be 64. And again, if you don't have these memorized, that's totally okay. Grab a calculator, maybe write down a list of tables and stuff like that. Let's see, this would be 4 to the third. So we're going to do 4 times 4 is 16 times another 4 is 64. 3 to the third, that's 3 times 3 times 3. So that's going to be 27. 5 to the third is 125. Let's see, 2 to the fifth, that's going to be 2 times 2 is 4, times another 2 is 8, times another 2 is 16, and times another 2 is 32. Again, that's a little bit higher exponent than we're used to, but again, powers of 2 come up quite a bit, so we want to know those. And then 10 to the fifth, if you want to check this, it's a 10 followed by 5 zeros. So it's actually 100,000. So that's a nice little trick. We count the number of zeros, that tells us what the exponent is. If we know what the exponent is, that tells us how many zeros there are. And then just a quick review of some of the rules for exponents. This is the product rule for exponents. So if we're multiplying two exponential expressions and they have the same base, we add the exponents together. So this is going to be 5 plus 2 is the exponent. So that's going to be x to the 7th altogether. If the quotient rule for exponents, we do a subtraction problem. We subtract the bottom from the top. So one way to handle this is just subtract the smaller one from the bigger one. So this is going to be, let's see, that would be x to the 5 minus 2. So this is going to be 1 over x to the third. Now, there is another way to deal with this. I'll come back and show you in just a second. And then rule is going to be really important for today. This is the power property, power rule for exponents. If I have a power raised to another power, an exponent raised to another exponent, what we do is we multiply those exponents. So this is going to be x to the 10th right here. So you'll notice we use the same exponents in each one of these examples, but because of where they were, we end up with a different answer because here we're multiplying, so we add the exponents. Here we're dividing, so we subtract them. Here we're raising a power to a power, so we multiply those. And then we've got negative exponents, of course. Negative exponents, that would be repeated division if you wanted to think of that. But really, the negative means reciprocal. So we're going to take this and we're going to move it into the denominator. So this is going to be x to the 5th right there on the bottom. So 1 over x to the 5th. And 7 to the negative 2. Again, the negative in the exponent means reciprocal. So that's going to be 1 over 7 squared. And 7 squared, I think we had this up above. If you really wanted to simplify that, if it's a relatively small number, you could write 1 over 49. So let me come back here. I'm going to change colors and we're going to look at this one. You could apply this rule here, the quotient rule. Some people will say, hey, you're always going to subtract the bottom one from the top one. You can totally do that. So this would be x to the 2 minus 5. Well, 2 minus 5 is going to be a negative 3 for an exponent. Well, we normally don't write answers with negative exponents, so we're going to write this as 1 over x to the third, and lo and behold, it's exactly what we got right there. So, quick review of exponents. That's how they work. And let's come down here and let's take a look at these examples. So what we want to be able to do is we want to be able to solve equations that look like this. So you'll notice that we've got an exponential, at least on one side, if not on both. And we want to use the equality property of exponents. So the equality property of exponents says this. Basically, as long as the bases are equal, then the exponents must also be equal. So what we're going to do here is we're going to rewrite each side so that they have the same base. Now, let me show you a really simple example of this. If I had, let's say I had 2 to the 7th equals 2 to the x. If the bases are the same, then the exponents have to be the same. So I could just say 7 is equal to x or x is equal to 7. That's really simple. If they already have the same base, then we can just drop the bases and just say the exponents have to be equal. Well, let's take a look at this one right here. This one's a little bit more complicated. So this one we have 8 to the m and 16. 8 to the m equals 16. Well, in order to apply this exponential property of equality, we've got to write these both as exponentials, and they've got to have the same base. Now, before you stop and think, oh, that's just 8 squared, that's not 8 squared, that's not how it works. Okay, 8 squared would be 8 times 8, so that would be 64. So here's the deal on most of the problems that we're going to work with. We're going to have to change both of them so that they have the same base. Now, in order to do that, I'm going to give you a little cheat sheet. This is just a little reminder. If you wanted to make one of these on your own, that would be totally okay. So these are some common powers with some common bases. So this is 2 to the first power, 2 to the second power, and so forth. So like 2 to the fifth, there's that 32 we dealt with before. If we had a huge number like this, like 2 to the eighth, that's 256. So here are the powers of 3. 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. We talked about that on the front. And 3 to the fourth is 81. And we can go through the list right here. This comes up quite a bit. You might want to know these. 5 to the first power is 5. 5 to the second power is 25. 5 to the third power, so 5 times 5 times 5, 125. Here are some powers of 6, some powers of 7, some powers of 8, and some powers of 10. And you could do more of those. Now, just kind of by way of review, let's make sure we're clear on this. If I have a number and it's raised to the 0 power, it's not 0, it's 1. So keep that in mind. And then what if the problem that we have to deal with doesn't appear on this list? What if we can't find it? It's not anywhere on here. Well, if that happens, then we're going to be dealing with our brain and a calculator. Now, I may pull out a calculator for some of these, but it just kind of depends on where we are. This list probably ought to serve us pretty well. So I'm going to come back over here, maybe take a snapshot of this or have this off to the side. We're going to come back over here and we're going to take a look at this. Well, I need an 8. I need to turn an 8 into some base, and I need the same base for 16. So we're going to come back over here, and what I want you to notice is you can look through here, and you can find an 8 over here, and you can find a 16 over there, but we need both of them to appear in the same list. And if you look at this, there's an 8, it's the same as 2 to the third, and there's a 16, it's the same as 2 to the fourth. So I'm going to come back over here, and here's what we're going to do. We're going to rewrite this as 2 to the third, and that's raised to the m. And on this side, that's 2 to the fourth. Now, we've successfully written both numbers, the 8 with a 2 to the third and the 16 with a 2 to the fourth, so they have the same base. But what I've got floating around here is this is still raised to the m power, mx, whatever the variable happens to be. So we're going to use this property right here, and we're going to use this a whole bunch. If I have a power raised to another power, I multiply those together. So this is 2 to the 3 times m. 2 to the 3m equals 2 to the fourth. Now, you'll notice what I've got here is I've got the same base. I've got 2. Well, this is the same issue I had up here, so I can drop those bases, and I can say 3m equals 4, and then I just have one step to finish this off. I want to get the variable by itself, so I'm going to divide by 3. We're going to cancel those, and I end up with 4/3, and that would be the answer. We probably want to leave it as a fraction. We don't want to write it as a decimal, 1.3 repeated or something like that. Okay, so in this case, we had to change them both. Relatively small numbers. I found on my list, I found, hey, there's an 8 and there's a 16. So those are the two that we're going to use. They aren't always next to each other, so just keep that in mind. So I'm going to come back over here. We're going to take a look at this one. Now, occasionally you might get lucky. So we need a 7 and a 49 in the same list. So I'm going to come over here. Let's look in the 7s. That seems like an obvious place to look. 7 is 7 to the first, and 49 is 7 to the second. So what's cool about this one, and you will get lucky occasionally, you only have to change one of these. This is 7 to the 3x, so that gets to stay the way it is. And remember, we're going to replace the 49 with a 7 squared. Remember, 49 is the same as 7 squared. So I'll come back here. 7 squared raised to the 4x plus 5. Those two are the same thing, okay? So this side equals that side. Now, this side's simplified pretty well. This side is not, so again, we're going to use this power property. If I have a power raised to the power like this, I'm going to multiply these together. So here's what I get. I get 7 to the 2 times 4x plus 5. Now, I'm going to show every bit of work on this just to kind of make it a little bit more clear what's going on. So I'm going to distribute through. So this is 7 to the 8x plus 10 equals 7 to the 3x. Now, it's true, I could have dropped the 7s right at this step, but I'm going to drop them right here, and this is what we're going to try and solve. So let me slide this down here. This is going to be 8x plus 10 equals 3x. I'm going to solve this by moving the 8x to the other side. I'm going to do that by subtracting 8x. I was thinking of the answer here. So 10 equals negative 5x. We're going to divide by negative 5. So we end up with x equals negative 2. So there's the answer to that. If I were to plug in a negative 2 here and a negative 2 there, they would equal each other. Okay, the two sides would be equal to each other if you threw that into a calculator. Okay, let's take a look at another one. We've got 25 and 125. I'm hoping that's a relatively easy one for people to remember. 25 is 5 squared. 125 is 5 to the third. So let's take a look here. This is 5 squared minus n minus 3. And this is 5 to the third. So again, I'm going to take a little bit of a step here. Power to a power, we're going to distribute through there. This is going to be 5 to the negative 2n minus 6 equals 5 to the third. So I just distribute that through because I'm power to a power. I multiply those together. The bases are the same, so I can go ahead and drop those. Negative 2n minus 3 equals, minus 6 equals 3. And then I'm going to add 6 to both sides. Negative 2n equals, this would be a 9, and I'm going to divide by negative 2, so we get n equals negative 9/2. Again, we're going to leave it that way, okay? We're not going to change that into a decimal or something. Now, let's take a look at these two guys right here. Need a 27 and a 9. If you think about that for a second, this is 9 times 3. 9 times 3. And that's 3 times 3. So if you wanted to break that down, that is actually 3 to the third. You could also just look on a list like this, or maybe throw it into your calculator, try powers of 3. And then on this side, we have 3 squared raised to the 5x, 5x plus 4. Okay, so don't forget that the 9 became 3 squared, the 27 became 3 to the third. There's only one side with a variable on it. It's this one. So this is the one we're going to have to take care of. So 3 to the third equals, this would be 3 to the, that would be a 10x. That would be a plus 8. So we'll finish this off here. I'm going to drop the bases. So this is going to be 3 equals 10x plus 8. Subtract the 8. So we get a negative 5 equals 10x. Get rid of that timesing by 10 by dividing by 10. Those are going to cancel. And when I throw that in a calculator, I stop and think for just a second. 5 goes in here once, 5 goes in there twice. So I get a fraction of negative 1/2. Totally okay. We got a whole number answer here. We got a fraction right here. Totally fine. Okay, now I'm going to change colors for this one because I want to point something out to this. Okay, this is 16 to the 2x and 4 to the x minus 1. Now, I want you to notice something. If we come back over here and we think about, hey, what would be the best way to do this one? I need a 4 and a 16 in the same list. Well, there's a 4 and a 16, so I could do the two of these. I could do this as powers of 2, but there's a 4 and there's a 16. So it's probably easier to use the bigger of those two bases. So we'll take a look at this one. This is 4 squared raised to the 2x. This is 4 to the x minus 1. Remember, we're using a base of 4. So this would be 4. 2 times 2 is 4. Got the x on there. 4 to the x minus 1. Bases are the same, so I can just drop those. I'm going to move this x to the other side by subtracting x. So I get 3x equals negative 1. And we're going to divide by 3, and we get x equals negative 1/3. I'm going to go ahead and put a box around that work. Say, okay, we got our answer there. But let's take a look at this. I'm going to change colors. What if we did try it the other way? We said we could have used the 2's. So let's write 4 as 2 to the second and 16 as 2 to the fourth. Let's just see what happens. So this would be 2 to the fourth raised to the 2x. And this one would be 2 to the second raised to the x minus 1. Okay, so we get, let's see, this would be 2 to the 4 times 2 is 8. This would be 2 to the 2 times x is 2x, and 2 times negative 1 would be negative 2. Bases are the same, so let's go ahead and get rid of those. So we get 8x equals 2x minus 2. We're going to subtract the 2x. So we get a 6x equals negative 2, and then we're going to divide by the 6. Those are going to cancel, and we end up, if you reduce that, we end up with negative 1/3. So you get the same answer either way. So if you've got a choice, it's probably easier to use the bigger of the two bases. Notice it was a bigger base, and we didn't have to change the 4. So that's going to make life a little bit easier. So if we take a look at the bottom here, go ahead and circle how you're feeling about this right now. And then I'm going to show you a problem from ALEKS. Okay, so we've got this one right here. We're going to look at that one, and we're going to say, okay, I've got 81 raised to the 3x minus 3 and 9 raised to the 8x. We need to write these both using the same base. So let's find a list that has both 9 and 81 in it. So we'll come over here. Let's see, I've got a 9 right there, and I've got an 81 right there. Okay, well, that looks pretty good. 9 is 3 squared, and 81 is 3 to the 4th. So I'm going to come back over here. This is 3 to the 4th raised to the 3x minus 3. And this is 3 squared raised to the 8x. Okay, so we definitely could do it that way. I'm going to write the work over here. So here's what happens. This is going to be 3 raised to the, that's going to be a 12x minus 12. 3 times 3x is 12x. 3 times negative 3 would be negative 12. And just multiply the two of those together there. That's going to be 3 to the 16x. Okay. So let's see, I get to drop the bases. So 12x minus 12 equals 16x. Don't forget that. Move the 12x over. So we've got negative 12 equals, this is a 4x. Divide by 4, and we end up with x equals negative 3. So the answer on this one would be negative 3. Now, like I was pointing out before, is there another way to do this? We'll take a look at this. 9 and 81 appeared in this list, but you'll notice I left something off right here. So if you want to use your brain and your calculator, let's fill this out right here. If we were to do 9 to the first would be 9. What's 9 squared? Well, 9 squared is 81. So if we came back here and solved this one and left this with a base of 9 and wrote this as 9 squared to the 3x minus 3, take a look at what we end up with. The bases are the same, so I'm going to multiply here. So that's going to be 9 to the 6x minus 6. And this is going to be 9 to the 8x. So this is going to be 6x minus 6 equals 8x. Going to move that over by subtracting 6x. Negative 6x equals 2x. There we go. And so we get x equals negative 3. Same answer either way. Okay, so lots to do here. The assignment is not very long. Good practice, good thinking here, especially with those rules for exponents. Good luck.